In the operation of a ship's power plant, steam must be used over and over again to conserve supplies of fresh water and fuel and thus increase cruising range. The endless process of turning water into steam, putting it to work, and turning it back into water is known as the steam cycle. It is a complicated and highly efficient system that has evolved over the years from the early days of man's use of steam. This rudimentary power plant, consisting of a simple boiler and an engine, had many disadvantages. It used a lot of fuel to produce steam of low pressure and temperature. The steam was lost after being used. This wasted fresh water and fuel, a serious matter where these supplies were limited. Periodically, the plant had to be shut down while the boiler was refilled. By connecting a large tank to the exhaust, much of the steam could be condensed for further use. Condensation was aided by adding a reservoir tank into which the hot water drained. Moreover, the hot water could be dipped from the reservoir tank and carried back to the boiler to go through the cycle again. This arrangement, then, involved 4 phases: generation of the steam, expansion to turn its heat energy into useful work, condensation of the steam back into water, and feeding of the water back to the boiler. Let's see how these phases have been developed in the efficient power plant of a modern vessel. In contrast to the primitive boiler, today's naval boiler is designed to get as much as possible of the heat energy out of the fuel and to produce steam of high pressure and temperature. Generation may be shown in this simplified boiler. The hot feed water enters a drum and fills several thousand feet of tubes. Underneath is the furnace with several burners. The burners mix air and oil in the right combination for complete combustion to produce maximum heat energy. The hot gases of combustion rise between tubes, which are arranged so that as much of the heat as possible is transferred to the water. Steam and hot water rise through the tubes, return to the drum, and are replaced by water from the drum, establishing a natural circulation of hot water and steam through tubes and drum. A boiler having only these simple provisions for converting water to steam produces what is known as saturated steam. This laboratory model shows saturated steam being produced. Saturated steam will have the same temperature as the boiling water, in this case 212 degrees Fahrenheit. No amount of heat can raise the temperature of the steam higher than that of the water with which it is in contact. However, if tubes are located away from the water, the saturated steam flowing through them can be heated to a much higher temperature. In this case, the steam has been raised to 312 degrees Fahrenheit. The process of adding heat to saturated steam is called superheating. In the boiler, the saturated steam is led away from the drum into a group of tubes called the superheater, which is located in a zone of high gas temperatures. Of course, this is a very simple type. Modern naval boilers are more complex, but all are based on the same principles of steam generation and superheating. The next phase, as we saw in the early steam cycle, is the expansion of steam in the engine to produce work. This engine, typical of those in modern naval vessels, is divided into 2 or 3 turbines, which turn the propeller shaft through reduction gears. As explained in the film, How Turbines Work, the rotors are set in motion by jets of steam. These steam jets are created wherever the steam passes through a nozzle or nozzle-like plating from a region of high pressure to one of lower pressure. Each drop in pressure may be compared to a drop in altitude, as in the case of a river pouring over a dam. Each drop produces the velocity to turn a wheel or wheels. Eventually, we reach zero pressure, or sea level. If we could lower sea level, we could put in another dam at the mouth of the river, and thus get more work out of the river. In the next phase of the steam cycle, we can do this very thing with steam by reducing its pressure below the pressure of the atmosphere. This final reduction in steam pressure is an important function of the condensation system. It is the condensation of the steam in the main condenser which causes this reduction to below that of atmospheric pressure and makes available extra energy to turn the turbine rotors. A laboratory experiment shows what happens in the condenser. The glass flask and its covering are filled with steam and sealed so that air cannot enter. Then the flask and its contents are cooled. This cooling condenses the steam, and something else happens. Condensation reduces pressure below atmospheric, as proved by the fact that the pressure outside pushes the covering into the flask. In the ship's main condenser, the steam is cooled by seawater, which is forced through small tubes. Here we're looking down into the compartment where the steam passes from the turbine exhaust to come in contact with the cooled tubes below. Through this opening, the seawater enters the supply header and feeds into the battery of cooling tubes, which we have just seen from a different point of view. The seawater emerges into an overboard header on the other side of the shell, without having had direct contact with the steam. In a condenser, designed for use on destroyers, there are no less than 20 miles of tubes. As the exhaust steam passes into the condenser, it condenses into drops of water through contact with the cooling tubes. The water, now known as the condensate, collects in the hot well. It is removed from the hot well by the main condensate pump. Air as well as condensate must be pumped out of the main condenser because air cannot be condensed like steam to form a vacuum. Air is removed from the condenser by a steam jet pump called an air ejector. Steam from the auxiliary line is fed through a nozzle, which causes a loss in pressure and a consequent gain in velocity. The steam jet carries along the surrounding air, establishing a vacuum which draws air out of the condenser. The mixed air and steam pass through the air ejector condenser, where the steam is condensed into water and the air is discharged to the atmosphere. Condensation is caused by passing the steam between cooling tubes, as in the main condenser. But here, the cooling tubes are filled not with seawater, but with the condensate, while on its way back to the boiler. Therefore, the air ejector steam jet not only removes air from the main condenser, but also gives up heat to the condensate. These, then, are the units of the modern condensation system: the main condenser, the condensate pump, and the air ejector. As we saw in the early steam cycle, the final phase is the feed system. In the modern naval feed system, the de-aerating feed tank does a big part of the job. For one thing, the de-aerating feed tank acts as a reservoir to supply feed water to the boilers under all conditions. Another highly important function of the de-aerating unit is to remove any air still remaining in the water. At high temperatures, air corrodes boiler tubes like acid. As the water passes through nozzles, it is broken into fine spray. In this way, air is released from the water and exhausted from the tank. The falling spray collects in a cone-shaped device and spills out through a narrow opening. Meanwhile, steam from the auxiliary exhaust line rushes into the same narrow opening and mixes with the water, heating it on its way back to the boiler. Pressure and temperature are raised step by step through feed and generation, just as they are lowered step by step through expansion and condensation. Two pumps, the main feed booster pump and the main feed pump, both working on the centrifugal principle, are used to push up the pressure in stages from the low pressure level in the feed tank to the high pressure level in the boiler. Another unit is the economizer, which further heats the water before it enters the steam drum. The economizer is located in the boiler, where it absorbs heat from the gases before they pass up the stack. The water entering the drum is ready for another trip around the steam cycle. The boiler also supplies steam for the auxiliary turbines and generates steam for the turbines which drive the boiler's air blowers and fuel supply pumps, supplies steam for the main condensate pump turbine, and steam for the turbines which operate the main feed booster pump and the main feed pump and other auxiliary turbines. The exhaust steam from these turbines goes to the deaerating feed tank. Here, as we have seen, it is used to remove air and to heat the feed water. The units in the steam cycle make a complicated pattern, but fundamentally the cycle is a simple one. The boiler produces high-pressure superheated steam. The steam is expanded in the turbines and turned into work. The condensation system condenses the steam, creating a vacuum, which makes more energy available to the turbines. Finally, the feed system removes air from the condensate, increases its heat, and delivers it to the boiler. Altogether, the units of these systems provide a continuous flow of steam and water, converting water into steam and steam back into water in a continuous and efficient cycle, thus meeting the all-important requirements of conserving fuel and fresh water and increasing the ship's cruising range.
Every naval vessel needs continuous, reliable electrical power to accomplish its mission. In this ASW task force, destroyer escorts, destroyers, and cruisers may supplement their ship service power plant with a Saturn gas turbine engine. In some ships, it drives a 750 kilowatt generator that can provide auxiliary power for routine operations or standby power when the ship's steam power plant is shut down. In other ships, it drives a 300 kilowatt generator and has the additional capability of automatic start should ship's power be lost in an emergency. The engine in both generator sets is the same. It uses the combustion of compressed air and fuel to rotate a turbine, which turns the shaft that drives the generator, thereby producing electrical power. Here we follow the practically instantaneous process as a series of separate events. Atmospheric air is drawn into the compressor first by power delivered to the compressor by the starter, then by power produced by the turbine section as combustion begins. The diffuser
by opening the drum blowdown valve for a few seconds. The separator is equipped with an automatic blowdown control that is adjustable for time cycle and length of blowdown period. During operation, any excess steam from the exhaust gas boiler is dumped to an atmospheric condenser by the steam dump unloading valve. When the boiler drum pressure reaches 105 psi, the valve opens to achieve rated flow of 12,845 pounds per hour, and then closes when the drum pressure falls to 100 psi. This action is accomplished through the pneumatic proportional and reset pilot controller mounted at the steam separator, which sends a pressure signal to the positioner valve assembly to open or close the valve. A three-way solenoid valve is included to close the dump valve upon loss of signal from a pressure switch in the cooling water line to the dump condenser. In the event that the steam unloading system is not operating correctly, the exhaust boiler is protected by an emergency dump valve which is activated by a signal from the ship's control system. The steam from the emergency dump valve is piped to the atmosphere. This valve is controlled by the excess pressure switch on the exhaust gas boiler control. For details concerning the design and operational characteristics of the exhaust heat boiler, refer to the appropriate sections of the V-Power Technical Manual. For more information on the steam dump condenser, consult the ITT Standard Tech Manual. Information on the steam dump unloading and emergency dump valves may be obtained in the Dresser Industries Tech Manual. The Circulatic Water Tube Boiler. The V-Power Circulatic is a quick steaming, horizontally fired packaged water tube boiler equipped with a modulating type burner and with a steam drum located apart from the burner firing zone. The boiler is located on the 23-foot level of the engine space, starboard side, just forward of frame 140. The circulating pump for the oil-fired boiler is located on the boiler skid and is driven in common with the forced draft blower by one motor. This configuration runs through the parallel connected steam coils, which are heated by hot combustion gases. The feed water to the boiler is supplied by the two feed water pumps discussed in section 2.0 of this tape. Water level control in the steam separator is maintained by a liquid level control, which creates a 3 to 15 psig pneumatic signal to a pneumatically actuated control valve. This system operates identically to the system found in the waste heat boiler. On a high air pressure signal of approximately 15 psi, the feed water valve will be fully opened. On a low air pressure signal of about 3 psi, the feed water valve will be closed. On pressures between 3 and 15 psi, the valve opening will be modulated. If the water level drops below a safe operating level, the upper level water control will open its contacts and de-energize the circulating pump motors. As with the exhaust gas boiler feed pumps, two stop probes are used to avoid nuisance stops of the circulating pumps from changes in water level due to ship's motion. Both probes must be above the water level before the level control contacts open. Once stopped, the circulating pump will not start again until the water level is restored and covers the pump start probe. Should the drum water level continue to rise, an upper level probe control activates the blowdown control to open its valve and prevent flooding the system. This boiler is equipped to operate manually or automatically for the initial filling of the drums and coils. In the automatic position, it is called on by a remote pressure switch mounted in the main steam header. The burner of this boiler is a forced draft automatically modulated type. Fuel and combustion air are automatically proportioned to each other over the complete burner range in response to variations in steam pressure by a variable type pressure element control. The control senses the steam, load, or pressure in the steam drum, then automatically causes the firing rate to be adjusted through the modulating burner control. This increases or decreases combustion air and fuel to the burner head according to the steam demand. An excess pressure switch with normally closed contacts in series with the burner circuit is installed in the steam sensing line. In case of excess steam pressure, the switch contacts open, cutting off the burner. Fuel to the boiler burner is supplied from a storage tank through a solenoid shutoff valve and fuel suction filter to a fuel oil reservoir on a fuel pump skid. The positive displacement fuel oil pump draws fuel for the reservoir through a manual shutoff valve and supplies it to the boiler. On this unit, there are two fuel pump and motor combinations that are piped in parallel. Pump number 1 or pump number 2 may be selected. However, only one pump can be run at a time. The V-Power Technical Manual contains detailed information regarding the design, operation, and control features of the Circulatic boiler. Consult this manual when additional information is required. Operation of the steam generating system. Integrated control system. The integrated control system is designed to supply and control the required amount of feed water to the exhaust gas boiler and the Circulatic boiler. Other controls for the exhaust gas boiler are also located at the integrated control system, but the fired boilers have separate controls for setting operational parameters and valve positions for generating steam. The integrated control system, which contains the controls for the common feed water pumps to both boilers, is located on the main deck. The control system requires a 120-volt AC 60 Hz power supply. To operate this system, first all 4 main disconnect switches must be closed. These switches supply main power to the 2 feed water pumps and the 2 recirculating pump motors. A control power selector switch is placed between the control transformer in primary winding and the main disconnect switches of the 2 feed water circuits. This allows either of the 2 sources of main power to supply the required 120 volts to operate the integrated control panel. Lights indicate which of the 2 sources are being used. Lights also indicate when each of the 4 main disconnect switches are closed. With the control circuit powered, circuits are completed to the low water control, alarm horn, low water light, the high water control, feed water air solenoid valve, and the automatic blowdown control. The feed water air solenoid admits air to open the feed water valve, which admits water into the drum. When the water rises in the drum to contact the low water level probe of the low water control, it will energize the low water control. The low water light will then be de-energized. To cancel the alarm horn, the start reset switch must be pressed. Next, the feed water selector switch is placed in the number 1 position. The feed water start switch is pressed and held. This energizes the feed water start relay. When the feed water pump light comes on and the feed pump is delivering water through the number 1 feed water pump flow switch, the start button is then released. The same sequence occurs if the feed water selector switch is set in the number 2 position. The transfer of these lights indicates that an automatic changeover has occurred. The recirculating pump operates in the same manner as the feed water circuits. To stop these circuits, the feedwater pump stop and the recirculating pump stop buttons are depressed to de-energize their respective pumps. Consult the operation section of the Vapor Technical Manual for further information about the integrated control system and its series of automatic functions. Exhaust gas boiler operation. As stated in the introduction, the exhaust gas boiler is capable of dry running. However, this procedure only should be used in case of extreme emergency. Therefore, operators must be prepared to operate the boiler before the main engine is started. Startup. To operate the boiler, all valves must first be arranged properly. Consult the operating instructions contained within the manufacturer's tech manual. Refer to schematic piping diagrams of Vapor drawing number 4860-3067 and drawing number 4860-6086. Remember that the exhaust gas boiler has feed water supply pumps common to the separately fired water tube boiler. Once all valves are positioned correctly, the control air supply is activated. The feed water pump and recirc pumps are brought online as detailed in section 3.0. Consult page 2 of the operating instruction for the exhaust gas boiler in the Vapor Tech Manual for the operating steps for filling the boiler. Once the boiler coils are filled with water, all the safety resets should be reset. Then the start reset switch on the integrated control system panel is pressed. The manual dump switch shown here must be in the on position. Next, start the flow of cooling water to the recirculating pump. The pump manufacturer recommends a cooling water flow of 15 GPM when the cooling water supply temperature is 95 degrees Fahrenheit. Cooling water to both recirc pumps should be supplied at all times that the boiler is operating, unless a pump is being serviced or replaced. If the number 1 position is chosen for all selector switches, the following white or green lights should be lit. The white power on light. The green feed water power on light. The green recirc power on light. The green feed water pump on light. The green feed water pump lead light. The green recirc pump on light. And the green recirc pump lead light. When these indicators are all lit, the system pressure controller is set to the required pressure. When the feed water pump and the recirc pump are operating smoothly and a stable water level is maintained in the separator, the boiler is ready to accept heat. The main engine may now be started. Remember, once the engine is started, there is no other method of controlling the steam output except by condensing or dumping the steam overboard. Shutdown. Warning, the exhaust gas boiler cannot be shut down until the main engine is shut off. Once the engine is shut off, the recirc pump stop switch should be pressed to stop the pump. Do not stop the recirculating pump until boiler cools down. Operation of the circulatic water tube boiler. Startup. Before attempting to start the circulatic water tube boiler, consult the operating instructions in the Vapor Technical Manual. The manual covers several pre-start checks, such as the following: modulator burner control dial setting, the cycling pressure switch, the drum water level, and the setting of the coil temperature control. Once these settings are correct and the boiler is filled, all manual resets are pressed. It's important to remember, do not attempt to fire the boiler unless it is filled with water. During normal boiler operations, position the valves as directed in the operating instructions contained within the technical manual. Also, keep in mind that the feed water bypass valve to the boiler is only open during manual filling of the drum. If the boiler needs to be filled, follow the filling procedures listed in the technical manual. Once the boiler is filled, it's ready to be fired. Firing the burner. If the burner is to be fired immediately after the boiler is filled, the operator simply leaves the main power switch closed and the circuit breaker in the on position. All the manual resets are closed and the fuel switch is placed in the oil position. Next, the start reset switch is pressed. At this point, the programming control will take over and automatically sequence the firing of the burner. Shut down. To shut down the boiler for a short period of time, the fuel switch is placed in the off position. The operator should allow the drive motor to run at least 30 minutes to cool the boiler down. Next, the panel circuit breaker is set to off to stop the circ pump motor. The boiler is now shut down. A time delay relay keeps the blower and water circulating pumps energized after the boiler has been cycled off. Consult the technical manual for the procedure for permanent shutdown and for other details concerning boiler operation. Section 4. Maintenance. Exhaust gas boiler maintenance procedures. Maintenance activities should be performed regularly as prescribed in the Vapor Technical Manual. Perform blowdown of the water level control and the sight glass daily. The drip well sump of the air pressure regulator also should be drained once a day. The feed water supply and water treatment system should be checked for proper operation, and feed water properties should be checked daily according to the procedure described in the tech manual. Also, the number 1 and number 2 feed water pumps and recirculating pumps should be alternated so that each pump is kept in serviceable condition. Soot blowers on the boiler should be operated daily or whenever the pressure drop across the boiler heat exchanger reaches 6 inches of water. The tech manual contains a section on boiler troubleshooting that gives possible malfunction indicators along with probable cause of each malfunction. Carefully consult this section of the manual and follow all maintenance activities recommended by the manufacturer. 4.2.